And before I start, I would like also to thank the organizer for taking care of this event, and thank you, Chris O'Malley, for inviting me. You have been trying to invite me in Mexico for a couple of years now, and finally we get to the point. For these two classes, I will talk about quantum contextuality and the geometry of quantum contextuality. And the idea is to start from a question which comes from quantum physics and which is relevant for quantum technology and quantum information, translate this to something geometrical and look at the corresponding geometry. And then this is what I will be basically talking about today. And tomorrow we will move to experience or proof of concept with quantum computers. Because you probably are aware that, quantum computers exist at least, theoretically. Sorry about that. Let me stop this. Yes. The question of quantum computers, it's an interesting question in itself, but they also exist online since 10 years now, and we can play with it as scientists. And I will show this tomorrow related to this problem. And for those of you who will be next week in Waraksa, I will do the same, but with a different physical problem, typically starting with entanglement, a different type of geometry, and different experiment. But let's start with today's talk. In the abstract, I wrote that the only basic thing that you need to know will be polymatrices. So I did write 2 slides to recall what are the important information, but I'm pretty confident that everyone is familiar with this. The 3 polymatrices X, Y, and Z that we will be talking about are given here. They correspond to Hermitian operators associated to measurement of a qubit in different bases. You have corresponding to the 3 directions of the Bloch sphere. And we have these relations on polymatrices. The product here is a product of matrices. There will be different product later on the talk. You have this product, so which X, Y, Z gives Z with the phase, and you have this property of anti-commutation. X times Y is minus Y. X times Y is minus Y times X, and so on. And as it will be a question in this presentation of measurement and observable, I just would like to remind that, the expectation of the observable Z for a given quantum qubit, so this will be just a single qubit, the formalism of quantum mechanics tells you can compute it by taking the bra of your qubit times your matrix Z times the ket of psi, and you get this equality, which gives you the expectation of measuring this quantum state in the Z basis. And if you change your basis, you change your polymatrices. And this goes to 2-qubit system. If, for instance, you try to measure EPR states, measuring the first qubit in the X basis and the second qubit in the Y basis, then in average you will have the outcomes of each measurement will be plus or minus 1, because you measure 2 qubits, but the calculation show you that this expectation should be 0. So far, so good. And also something which will be important for the talk today is that one of the important things in quantum mechanics is that in order to know that the value of the position of a qubit according to the Z direction, you have to perform an experiment. You have to make a measurement. That's why we have this concept of observable. You cannot pre-assign the value of what will be the result of your experiment before you do it. Okay, and this is will be important for what comes next. Okay, so there will be 3 slides important for this talk today, and probably tomorrow 2 or 3 slides as well. One is about the Cohen-Specker theorem. So who knows what the Cohen-Specker theorem is? Okay, good. So there's plenty of students, and I hope you will at least get an intuition of what this theorem is. And the first slide will probably not be very explicit. The first slide says the following. First, I need a definition. So I consider a family of observables. Okay. And we will be mostly talking about multi-qubit Pauli observables. So take, for instance, like before, 2 qubits observables. If these observables are, you can define a subset of observables which are mutually commuting. And this subset of mutually commuting observables, I will call this a context. Okay? And basically a context, it's an experimental setting where the observable can be jointly measured, meaning that the measurement of one observable will not disturb the measurement of the next observable, because the matrices commute, basically. So what the Cohen-Specker theorem, it's a theorem that was proven in 1967, it said that it's not possible to have a hidden variable model that reproduces the prediction of quantum mechanics if this model is independent of the context. So the first time you see the theorem, it takes a little bit of time to understand what it means. It doesn't mean there is no hidden variable theory. It's possible to have a hidden variable theory that reproduces outcomes of quantum mechanics, but this model should be context dependent. The predefined value that you will assign to some observable should depend on the context in which you consider the observable. So it means if you measure the property of something and you want a classical model that explains this, well, some property will depend on the other experiment you will consider compatible with this property. And if you change the set of compatible experiments, it may change the value of your result in your hidden variable model. Okay? So the first important slide is the next one, because this theorem that we cannot understand when you see it for the first time, we're going to prove it. And once it's proven, you will at least get the feeling that maybe we understood a little bit what it was about. So I'm going to show you a proof which was proven by Asher Perez and David Mermin. I also have a slide with all the references for concluding the talk, so you will be able to get the information. And the Perez-Mermin square is a collection of 2-qubit observables arranged in a family of contexts, so set of commuting operators, as follow here. So I will write down this square because it will be useful also later. So you have 9 observable. So I choose YZ. So here, when I write YZ, it's not the matrix product. In fact, it's a tensor product. It's one observable for the first qubit, one observable for the second qubit. Okay? So you measure your first particle in the Y direction, the second in the Z direction. Then for this observable, it's ZY. Here it's XX. Here, this is ZX. Here, this is XZ. Here we have YY and XY. YX and ZZ. And all the observable which are on the same lines or column, you can check that they mutually commute. So they form context, set of mutually commuting 2-qubit observables. You do the calculation. You can also check that if you do the product of this observable here will be plus identity. The product of this observable here will be plus identity. The product of the observable here will be plus identity. And here it's in fact minus identity, minus identity, minus identity. And now suppose you have a classical model that can reproduce the outcomes of quantum mechanics. So a classical model that can tell you in advance that measuring my system, measuring the first qubit in the Y direction and the second qubit in the Z direction will give me +1. So +1 for the first particle, +1 for the second particle, it's +1 for the 2-qubit observable. Suppose I have this. It would mean I could fill this square with plus and minus 1 in such a way that the product of my plus and minus 1 should also satisfy the constraint given by the lines and column, because quantum mechanics tells you also that the product of the eigenvalue should be an eigenvalue of the product of the observable. Here the product of the observables are plus identity or minus identity, meaning that the product of the eigenvalue should be +1 or -1, depending if I look at the line and columns. So the game is the following. You have 9 nodes. Each of them correspond to a 2-qubit experiment, which will produce plus or minus 1, depending how you measure each of your qubits. And you have 6 constraints. If you measure the qubit following the first context, the result should be +1. The second context +1, third context +1, and then the colon context should be -1, -1. You try to do that as much as you can, you will never success. It's what's represented by this square here, okay? So you see we assign +1, +1, +1. It gives me +1 on the line, that's correct. I assign +1 for the measurement of the x, -1, -1. This gives me +1. I assign -1 here, +1 here. The columns here are correct, it's -1, it's correct, it's -1, but now I have a problem here. I cannot satisfy the constraint of giving me +1 here and the constraint of giving me -1 here. It's not possible. So it doesn't say there is no hidden variable model. It says if I have a hidden variable model that explain and reproduce these outcomes of quantum mechanics, my model should give me a different result for this observable if I consider this observable inside this context or this observable inside this context, which is a little bit counterintuitive. Because if you want pre-assign some value, you don't want this value to depend on some experiment that has not been made already. Okay? So did the grad student learn something about the magic square? It's a very nice picture. I like it very much. So I hope you enjoy it. And by the way, it's not. It also has a lot of implication. Like there is many work on quantum context. Well, tomorrow we will talk about experiment we can do with it. But there is also several things about quantum contextuality as a resources for quantum communication and also to speed up quantum computation. So it's a very deep and profound subject. All right, so now we're going to move to, if there is no question on V square. Yes, please.
So your observables are classical objects. You say it's X, it's Y, it's Z.
It's 2-qubit Pauli matrices correspond to observing or measuring the spin of your first particle in the Y direction and in the Z direction. And
so is there a version of this where X, Y, Z are sort of quantum variables, so there can be superpositions?
I don't know.
Okay.
I know. For me, that just 4x4 matrices representing observable, so representing some experimental settings. And what quantum mechanics predicts, which is given here, cannot be reproduced by a non-contextual hidden variable model. Yes?
It's so strange because they commute only, they form actually so-called stabilizers. They commute only along lines and columns. But if you pick arbitrary operators, they do not commute. So there is sort of correlation, of course.
Yeah, of course.
Correlation.
I mean, the reason there is something, and we will see this in the geometry, is because these two guys does not commute. Here and here and here and here. Yeah. And quantum mechanics does not say that there is something special about V square. All these measurements are predicted by the theory. The thing is, if you want a hidden variable model that reproduce this, your hidden variable model should be very special in the sense that the predefinite values should change depending on which context you consider. And this can be tested experimentally. So there is the main message of this theorem is that there is no, it's a kind of no-go theorem. There is no non-contextual hidden variable theory that can be compatible with this. Yes. But the obstruction to have a classical model is because this guy does not commute.
Yes, sure. You can measure this and forget about this sort of and then. Okay, so you have two contexts in which they in both cases they all commute.
Mm-hmm.
And this in a sense, this other contexts are hidden from this.
Okay. Okay. Okay, good. So now let's go to the geometry and talk about the geometry of commutation relation, because contexts are defined by commutation, and there are some geometry behind it that I would like to describe yes. Okay, so now I'm going to talk about the generalized n-qubit polygroup, which is the group of n-qubit poly operators where AI, AN are polymatrices, including the identity. You consider the tensor product, and you have a phase which is plus or minus 1, plus or minus I. Okay? So it's the same as before with my 2-qubit operator, but now I take n-qubit operators. And each single qubit operator, each AI, can be seen as a product here. This is the matrix product of Z and X with some exponent. If you take 0, 0, you get the identity. If you take 0, 1, you get just the matrix X. 1, 0, you just get the matrix Z. And then if you take X, Y up to a phase, you take 1, 1 up to a phase, you get Y. So there is a coding, a way of coding each polymatrices by a doublet of integer in Z2. So this defines a map that allows you to map one n-qubit observable to a plate of element in Z2 of collection of 0, 1. Okay? What can we do with that? Well, in fact, if we mod by the phase, we get an isomorphism, and you can map any poly operators up to a phase to a vector in Z2 to the power of 2n. So here's an example with 2-qubit operator. So this matrices, again, remember, when there is no product, no sign, it's tensor product. So X, Y, and ZZ lives in P2, the space of 2-qubit poly operators. If I do the matrix product of these two guys, I do the matrix product of these X and Z, Y and Z. If I follow the rules I introduced before, it's minus IY, IX, and up to a phase, this is just Y tensor product with X. Okay? Well, if you use the map, remember X is encoded by 0, 1, Y is encoded by 1, 1, so you get this 4-component vector, and Z is encoded by 1, 0, 1, 0, so you get ZZ. And now you take the sum mod 2 of these two vectors, 0, 1, 1, 1 plus 1, 0, 1, 0, you get 1, 1, 0, 1, which is exactly the image of YX, because Y is 1, 1, X is 0, 1. So this map maps your n-qubit poly operators to vectors, and it maps your product of operator to sum. Okay? And there is a little subtlety. We can move to projective space, but projective space over Z2 is very special because you have only one scalar, which is 1. So basically, projective space here means you forget about the 0 vector. You take all vectors except the 0 vector. And so our map maps n-qubit operator modulo phase to points, and it transforms the product to sum, but the product was responsible for the non-commutativity of the observable. So we broke, in fact, so we are happy with that construction, but we lose the main important information, the commutation relation. Okay? So it's very nice, you map the operator to point in some geometry, but by mapping the product to sum, you lose one important information, the one about the commutation and non-commutation. So we need to recover it. So the next step is how we're going to recover the information about the commutation. Okay, again, I do an example with n equal 2, but you can do it. It's a nice exercise for the student to do it for n. And here is 2 observable in P2. Again, I wrote them as a product of Z of X with some alpha i's. Okay, so depending on your choice of alpha i's, you will get either identity, X, Y, or Z, and the same here. And now I take 2 observables with different parameters. And if you write the result of the product of O times O prime, matrix product, and O primes times O, there will be some phase that will show up. And by just asking the phase to be equal, you will end up with this relation here. Okay. So again, it's a direct calculation. I invite you to try this calculation. Just write O times O prime. You see, you will have this matrices times this one, but you know that X and Z, if you ask X and Z to commute, you will have a phase which depends on the product of B1 and alpha 2 prime, which is, what is it? Sorry, beta 1 and alpha 1 prime, okay, which will come from here. Again, it's a straightforward calculation, but the point is this relation here define a symplectic form on the space, which is encoded here, and the two observable in the polygroup will commute if the corresponding point downstairs or in your projective space are isotropic or annihilate the symplectic form given by this relation. Okay? So we recover this important information of encoding the commutation relation in your n-qubit polygroup inside your projective space by adding some extra structure, which is here a symplectic form. Okay? So that's where the geometry will come from. Okay, so now maybe comes the second important slide of the talk. No, not yet. This is one more general consideration before we start to example. So the symplectic polar space is the final object we want to deal with. Up to a global phase, a non-trivial n-qubit polyoperator corresponds to a point in the projective space. More explicitly, you have your operator here. So I forget about the phase and I encode my n-qubit operator by looking at the two n vectors of 0, 1 coefficient here. And two operators will commute if and only if they annihilate the corresponding point, annihilate the symplectic forms. So the commutation is encoded by isotropy with respect to the symplectic form. And now you equip your projective space with this symplectic form, and you define what is called the symplectic polar space of rank n over the two-element field, and which will be denoted for the remaining part of the talk by this W2n minus 1, 2. Okay, but the important point here is commutation relation in my n-qubit polygroups becomes collinearity or isotropy in this new space that I call symplectic polar space. Okay, so now comes the nice example. All right, so this is the first geometry to discuss. It's called the doily or W32 or the symplectic polar space of rank 2. It's so it's a geometry which contains 15 points and 15 lines. It's given by this configuration here. And it's a geometry which encodes all commutation relation of the two-qubit polygroup. Okay? So you see here, for instance, XX, YY, ZZ. This is exactly this context here. Okay? What can we say about this geometry? So it's what we call a 15-3 configuration, because each line contains 3 points and each point contains 3 lines. Okay. It is a unique out of 245,342 configuration, which is triangle free. So it's called the generalized quadrangle, because if you take 3 points, you cannot join them directly. You except, of course, if they are on the line, but 3 points which are not on the line. So take this point, and this point. Then you cannot close. You cannot make a triangle. Okay. If you want to connect with this guy, you have to go here, 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 and here. You have to make a quadrangle. Okay. It's called a generalized polygon because the smallest way of connecting non-collinear points is by making a quadrangle. So it's a generalized quadrangle. And again, as we mentioned earlier, the fact that it's triangle free is what makes this square. So here you see in red, this is exactly this Mermin square. The fact that there is no triangle is which makes this square contextual. Because if this observable were, like if I could join here in this geometry, these 3 points, there will be commuting. And in fact, everything will be commuting and everything will be a context, and there will be a classical model that reproduces the outcomes of quantum mechanics. No problem with that. If I limit to one context, I can find a classical model that reproduces the possible outcomes, which is compatible with outcomes. Okay, and the second information I like to emphasize is that, okay, so the Mermin square here is a subgeometry of this space. Okay, so this proof of Cohen-Specker theorem is a subgeometry of this configuration, and in fact, it's what we call the quadrics, meaning it can be defined by a degree 2 equation, and quadrics in symplectic polar space have been studied. We know the number of points, number of lines in any dimension. There is a literature of finite geometry about this kind of object. Okay. And there are 10 different Mermin square that can be located in this picture. Okay. Questions about this? Yes. Yes, that's the next slide. Yes. Okay, I think I'm not sure. Okay, I'm going to try to answer, but I'm not sure I'm answering exactly what you think. Another picture which is behind this is if you map, like remember in my construction, I first started by mapping the observable 2 points in the vector space. Yes, yes. So if you just do this, and you don't add this symplectic form, you take as a line the fact that A plus B equals C, and you say ABC is a line. Then you will not get 15 lines, but 35 lines, and you will get the full projective space. So you get a richer geometry. So what happened is we took this full geometry, which is defined by the abelian group or the vector space Z, so here Z4 over Z2. Okay, it's defined a full geometry. So first we restricted by removing 0, 0 by going to the projective space, which corresponds to forgetting about the trivial Pauli operator. Okay, and then we put this symplectic form which erases some of the line which do not correspond to commuting operator. But if you take the full space and you consider all the lines, you have a geometry which is different from this because you will have lines between every element, every couple of elements. Okay? Does it answer your question? Okay. Sure. Okay, so now for your question, let's go to n equals 3. So what happened with n equals 3? For n equals 3, we can define also the symplectic polar space of rank 3, which is called W52. Okay, to remember, it's W2n minus 1, 2. And this geometry encodes the commutation relation of the 3-qubit Pauli group. But this geometry is a little bit more interesting because now we have 63 points and 315 lines, and we have plane 135 totally isotropic plane, which is called a Fano plane here in finite geometry. So here's an example. I'm sorry, it's a little bit small, but you see the operator YYX, ZIZ, and XYY. You can check that they all mutually commute, and this is a line. This circle here is a line. Oh yeah, I forgot to say, but I hope you are not. This was a line. Yes. Everything which connects 3 points is a line. So here it's the same. In the Fano plane, this circle here is a line. And in fact, everything is commuting here. And now, in this picture, and I'm really sorry that the operators are so small, but I will provide the slide if you want to look closer. This configuration is called the Mermin pentagram. And it's another contextual configuration made of context made of 4 observable. In fact, the context of these 4 observable here correspond to 4 elements in my Fano plane. So basically, if you remove, so what can you see in this Fano plane? If you make the product of all 3-qubit observable, you will get plus or minus identity. And the same is true for the line. So if you remove a line, you are left with 1, 2, 3, 4 operators which mutually commute and whose product is plus or minus identity. So you can make context with 4 elements of your Fano plane. For the one who are familiar with finite geometry, this is a projective space this is a projective plane, and if you remove a line, you'll get an affine plane in finite geometry. But if you take this 4-element or this affine plane, you get one of these contexts here. And Mermin, in the same paper, proposed another proof of quantum contextuality using this so-called Mermin pentagram, but which can be seen in W5-2 as a collection of Fano planes that intersect with some property. Okay. So this subconfiguration provide other contextuality proof beyond the Perez-Mermin square. And I have one more crazy example. So again, you cannot read this, but this is called the split Cayley hexagon of order 2. It's a geometric configuration made of 63 points, 63 lines. And all the lines here correspond to isotropic line in the symplectic polar space, so mutually commuting operator. And this, in fact, was known by geometers since the 19th century. It's an example of a generalized polygon. It's called an hexagon because you can never connect 7 elements directly. If you have 7 elements, you cannot close. You need to take an extra one to like you are. Like there is no triangle in a generalized quadrangle, well, the smallest, sorry, you cannot connect by 5. There is no pentagon inside this geometry. Okay, so at this stage, this is more like an exotic geometry that you find in this context of studying commuting relation of 3-qubit polymatrices. And if we stop here the story, you can say, well, this is nice. In fact, this is, as I told at the beginning, when I started to work on quantum information, and before I was trying to make experiments with quantum computers, I was describing some phenomena with geometric objects, and a lot of my physicist friends were telling me, oh, this is very nice, beautiful construction, beautiful configuration, but what is it good for? I mean, what is the physical meaning of this? And this was discovered like 15 years ago by Method Saniga and Peter Levi, two collaborators of me. And I agree, it's very beautiful, and I was very happy to work with them on this. But what does it tell us about contextuality? So tomorrow I will tell you what this configuration in particular tells us about contextuality. Okay, so that's the end of the part of the geometry. So we have Cohen-Specker theorem that has an interpretation in terms of context and observable in context, the Mermin square proof. You can embed this in some larger geometry, and then you get some new configuration. And with this new configuration, you can try to see, can we build some other proof with more observable, more context, and connect this proof to some interesting and exotic geometry. And now, the last part of this talk, I want to discuss the part on the algorithm. How do we prove that a given configuration is contextual? Okay, how can we prove? Well, we did prove for the Mermin square because it's easy, but if I have a much complex geometry with much more observable and much more context, how can I efficiently prove that it is contextual, that there is no assignment? Okay. So that's the third important slide that I would like you to get from this talk. And this is the way that we tested with my collaborator if a given configuration is contextual. So a simple algebraic test to determine whether a configuration is contextual or whether a configuration will provide a Cohen-Specker proof like the Mermin square. So for the Perez-Mermin square, we suppose that each observable is assigned with a predefinite value, Vi, which is plus or minus 1, and the row and the column constraint give us this system. The product of the eigenvalue is plus 1 for the line, and it's minus 1 for the columns. If you just switch this in the binary algebra over the two-element field using Vi is minus 1 to the power of xi, this relation becomes a linear system with Boolean variable x1 XOR x2 XOR x3 equals 0. This sum here is the sum mod 2 of the XOR in computer science. And if you add all these 6 equations, because you want these 6 equations to be satisfied, you want to find some value xi's that allows you to satisfy all these 6 equations in the same time. Well, if you suppose that these 6 equations are satisfied, you get 0 equal 1. So what it says that this system of algebraic equation has no solution. Okay? You have a system that has no solution. So here it's easy to prove. How do we prove usually that a system has no solution? A system of equation has no solution. Okay, we're going to see this in a minute. Okay, so how can we generalize this? You suppose you have a configuration which is made of n observables, n node, and m context. So the context, again, are the constraints. Okay. I assume that L of them are positive. So here I have 3 positive contexts and 3 negative contexts. To test contextuality, I can rewrite all my conditions inside the linear system AX equal B. For the Mermin square, my system AX equal B is this one. I have a 9-dimensional vector, x1, x2, x3, x4, x5, x6, x7, x8, x9. And then I have a matrix which is 6 lines and 9 columns. Okay, because I have a vector of constraint. The vector of constraint is 0, 0, 0, 1, 1, 1. So here, my vector B is 0, 0, 1, 1, 1. My vector X is x1 up to x9. This is what I would like to find. And my matrix A is the incidence matrix of my geometry. It tells me if a node is in some given context. And you can encode this. So again, X is a vector, n-dimensional vector over Z2. A is a m by n matrix. So m context for the line, n column for to be compatible with this vector. A, J, I equal 1 if the observable I belongs to the context J. And the vector B1 up to Bn correspond to the constraint 0 if you have a positive context and 1 if you have a negative context. Okay? And to decide if the configuration is contextual, you need to check if AX equal B as a solution. And this can be achieved with the Gaussian elimination. We have an algorithm, the Gaussian elimination, that allows you to answer this question with a complexity m square n, which is okay for the application I will show you in a minute. But there is another question which is more interesting than just deciding if the configuration is contextual or not, is to decide how much it is contextual. How bad is the situation? How far are any classical model incapability of reproducing the prediction given by this configuration? In other words, how many values should I change? How many values should I change to make this system to find a solution of this system? Okay, so one question is this system has a solution or not? We have an efficient algorithm. The other solution is how many value, the other question is how many value of B should I change? What the minimal number of value of B that I should change in order to make this system possible. Because you see, if one of the reasons that we have problem here is because you have context of different sign. If everything was plus identity, I just put 0 everywhere and my system is or plus 1 everywhere and my system is satisfied. Okay, so the distribution of negative line and where the distribution of the negative line will be, the position of this negative line will produce this contextuality. So again, I repeat, the difficult question is what is the minimal number of B that I should change in order to make this system satisfy? So the degree of contextuality is exactly this quantity. So the degree of contextuality is what is the minimum number of entry of B that must be changed to make the system consistent. And now if you want to brute force algorithm, you have to try every single B and change every B from 0 to 1 until you check a solution. And now the complexity is very bad. It's 2 to the power of m. It's exponential with the size of your vector B. So there is no efficient algorithm or no deterministic efficient algorithm to compute this degree of contextuality. And tomorrow, when I will talk about experiments, this degree of contextuality will be important to measure how far your system is from a classical model. This, in terms of experiment, is what we'll be able to catch and measure in an experiment. Here are some results. So the Mermin square, we already discussed, 9 observable, 6 contexts, degree is 1, everyone, well, we did the proof, yes. We did the proof because, okay, we prove it's contextual with the system. We add all the line of the column, we find 0 equal 1, there is no solution. And if I switch this minus identity to plus identity, then I can find a solution. Because remember the square we had at the very beginning, everything was satisfied except this one, but if I switch this minus identity to plus identity, then I can find a solution. So I just need to switch one value to get a system that could be satisfied, so the degree is 1. For the doily, remember this beautiful 15-3 configuration, the degree of contextuality is 3, and you can, in fact, the system is not too large, you can solve it with a brute force algorithm. You can search, that's how we found it at the very beginning. For the full symplectic polar space of rank 3, for the 3-qubit poly matrices, now you have 315 contexts, so you have 315 constraints. So if you want to apply a brute force algorithm, you have to try 2 to the power of 315 configuration. And that's not possible. Okay. So, but we know the degree, and in fact we prove with my colleague Alain Giorgetti and Method Saniga, but mostly the work of our joint PhD student Axel Müller, who developed a heuristic algorithm to compute degree of contextuality, and we were able to prove that here the contextuality is 63. And maybe to make, you have a question?
What's the maximal degree for a particular geometry?
For a given geometry? Well, okay, so I'm going to show you a reference where we have some table with computation for 4, 5, 6 qubit, but the maximum that we know, for 4 qubits, the geometry is like huge, and we have some bound on the degree of contextuality, but we don't have the exact value. The last exact value that we have is for n equals 3. And we have some value for subgeometry of here. If you consider quadrics inside this space, we have some values. But just to make some advertisement for tomorrow, 63 constraints, meaning so there are 63 special lines in this W53 geometry, W52 geometry. So maybe you can guess, or you can try to guess for tomorrow, what could be these 63 special lines, okay?
It seems to be 2 to the n minus 1, the degrees, no?
Yes, but you know, it's only 3 examples. And of course, if I show you some subgeometries, the degree change. I mean, it would be very nice to have a formula. Okay, and then maybe to conclude, I put some references to tell you where this different type of information comes from. So the original paper of Coren Specker that introduced this concept of contextuality was, as I said, published in 1967. They don't talk about 2-qubit poly observable, and they don't talk, of course, about magic Mermin square, because the original proof is very different, much more challenging to understand. It's a configuration of vector representing projector, and they prove some that there are some incompatibilities. Okay, so but it's originally comes from here. Mermin and Perez in the same years propose this operator-based proof of contextuality, which is the one I talk about today, and I will keep talking about tomorrow. I mentioned Method Saniga and Peter Levi, 2 of my very close collaborators. They have been working on this type of geometry since more than 15 years now. And in this paper, they describe configuration of 3-qubit observable and hyperplane in the smallest split scale hexagon. This is a paper where we introduce this notion of a degree of contextuality, and we obtain, so it was in 2022, and we obtained some result on degree of subgeometry of this space, but in 2022 we were not able to do this calculation. And in fact, there were some results published in the literature, but which at the end turned out to be wrong. People believed that the degree was just the number of negative line, which is 90 here, but it turns out to be incorrect. So it was very recently, I forgot the year, but 2024, where Axel implemented a specific heuristic to well, if he did some preliminary work on SAT solver, because it's related, this type of Boolean system, to SAT problem, but end up at the end to develop a special heuristic to find the bounds on degree of contextuality, and we were able to prove that for the W52, the exact degree is 63. So that's about what I wanted to say for today's lecture. Tomorrow I will come back to this contextual configuration, but I will talk about an inequality on the measurement that is called, that is due to Adam-Cabello. And this inequality relies on this degree of contextuality. And this inequality allows you to propose an experiment that separates quantum mechanics to a non-contextually done variable theory. And then I show you how we can make this some experiments to make this measurement with the quantum computers. And if time allowed, I will also talk about quantum games, because there are quantum game scenarios related to this configuration as well. Okay, thank you.
Any questions?
Hi, thank you, Frederick. Is there a characterization of all the possible configurations that are non-contextual, at least for 2 qubits, for example?
Yes, there are some results. Okay, for instance, in 2 qubits, you can, so there are some very natural subconfiguration that we can discuss in this space. One is, for instance, studying the different type of quadrics. So in finite geometry, there are a lot of concepts that merge together because of the finite dimension. So quadrics in this space are also hyperplanes. And hyperplanes, so maybe let me choose this definition because it's intuitively easy to understand. A hyperplane is a collection of points in your geometry such that every single line of the global geometry is either contained in your upper plane or intersect your upper plane in one point. Okay? So look at the Mermin square here, which is red. It's an hyperplane because if I take this line, it intersects here. If I take this line, it intersects here. Now if I take this line, it's fully contained. So it's a hyperplane in this sense. There are 2 other types of hyperplane in W32. Another type of hyperplane is you fix a point and you take all the line collinear to the point. You see? So this is also an hyperplane. You can check that every single line intersects this configuration. It's called in finite geometry a perp set because basically you take everything which is collinear to this guy. Well, this configuration, this perp set, is not contextual. You can assign some value, and in fact, it's not contextual in any dimension. There is another funny type of hyperplane here in this geometry. It's called a novoid, and it's an hyperplane which contains no line. You take this point, this point, this point, this point, and that point. No, and that point. Am I correct? Yeah, I think that this, and this. And then every single line will intersect this geometry, but this geometry has no line, so you have no context, so you have no okay. So in the different paper we developed with Axel and Alain. So we have all of this colleague, we have a couple of papers, and in some of them we have like table, because Alain was a computer science student. Alain is a computer scientist, and Axel, who was his PhD, was a computer science student. So we generate bunches of table with result on contextual and non-contextual configuration, and when possible, bound on the contextuality degree.
Thank you.
Any other question?
Is there any relation to the mutually unbiased basis of this construction?
Yes, they are, and okay, well, yeah. So Method Saniga, my colleague, who in fact introduced me to this subject of finite geometry and encoding the commutation relation inside the symplectic polar space, has some paper on mutually unbiased base, but I'm not sure I will be able to explain it right. I know there are some connection. There are also some connection with stabilizer state. There is a team who developed some work in the 2010 something, how to use this encoding with Z2, the very encoding I proposed at the beginning. So they don't talk about the symplectic polar space, but they use, well, actually they do, I think, but maybe not exactly like we said. Where's my map? Yeah, so they use this map here to discuss stabilizer state, because stabilizer state are defined by abelian subgroup, which will be here an isotropic subspace, like the Fano plane I show in the 3-qubit picture is in fact a model for a maximal abelian subgroup of 3-qubit operator. So it defines a unique stabilizer state. So all the literature on error correcting code, there are some correspondence with this for different reasons, but the same geometric mathematical construction.
Any other question? Okay, how intensive are those calculations in computer?
They could be very intensive. For instance, if you try to have a proof of this degree based on a SAT solver, so something which will test different different scenario to assign the value of your system. I think it was like something like 20-something hours of computation. But then we found an heuristic that does it in a couple of seconds. Yeah, it's very challenging. At the very beginning, we were so happy with this description and to be able to prove that some configuration were contextual. But then at some point, we were very frustrated to not be able to calculate the n equal 3 case. So, yeah.
Then let's thank our speaker again. So we resume tomorrow at 10